Greetings everyone and welcome back to the bench. Time to move ahead on the discrete audio amplifier design and build project. This time we're going to get into the voltage amplification stage, or VAS as it's called. Now if you've been following the series, you know I started out with the input stage, then I jumped over the VAS to the output stage. Then now I'm coming back to the VAS. The reason for that is the layout of the output stage kind of dictates the way this VAS stage is set up. So I thought it would be better to get the output stage out of the way and then move on with the VAS. Now this video is going to cover constant current sources as used in the VAS stage. However, it would be nice to kind of introduce the stage before I move ahead with that. So the VAS stage, at least the way I'm going to present it, does three different things. First thing, it takes the signal from a previous stage, in this case from the input stage, and amplifies it through this transistor. This transistor is set up with a class A bias, and it has to make the voltage swing very large. In fact, it has to swing nearly rail to rail. The reason for that is because the output stage doesn't have any voltage gain. The output stage is all about current. A vast majority of amplifiers these days have emitter-follower type or complementary feedback type designs. And in fact, most of the engineers and amp designers frown upon output stages with voltage gain. So these stages are designed so they only provide current, no voltage gain. So it's up to the VAS stage to make that voltage swing as large as it can possibly be before it gets into the output stage, because you need a large voltage swing to drive your load to get the most output power. I should mention at this point that this is a very minimalist drawn diagram here just for the purposes of explanation. I left out some of the components and it might even change. The second function of the VAS stage is the biasing network. Though some people might consider it a separate circuit, but because it's in the current path of the VAS stage, I consider it part of the VAS stage. So what happens is you have the base emitter junction diode drops around the circuit here. So you need a circuit that sets the voltage at these base points, you know, the upper transistor driver base and the lower transistor driver base. Set that just enough to let current flow through the amplifier like this, which turns the output stage on with a bias. And you do that to eliminate crossover distortion. Also, as these transistors heat up during use, you want this to thermally track that and keep that bias relatively constant. And now the third and final function of the VAS stage is the constant current source. Arguably not as important as these two. I mean, you could just replace it with a resistor. However, in a hi-fi amplifier, you don't really want to do that. And this is mainly what this video is about, the constant current source, and we'll take a look at a couple of them and see which one will work the best. But what are the properties of a constant current source? Well, one thing you can probably guess, it keeps a constant current. As I said previously, there's going to be a very large voltage swing in the VAS stage. So regardless of that voltage, we want this to deliver a constant current. That way the output stage always gets the correct amount of current it needs for driving the load. Another property of the constant current source is infinite impedance. Well, in the real world it's not going to be infinite, but it's pretty high impedance. So it doesn't impress a very heavy load on this transistor here. In other words, it allows that voltage to swing freely. And a third property of the constant current source in the VAS stage is it has to have a low dropout voltage. Remember, that when this voltage is swinging towards this rail here, the voltage drop at this point to the rail is going to be very low. And if this constant current source dropped out, in other words, stopped the regulating current, the current would fall, and now this part of the output stage wouldn't be able to deliver current where it really needs it at the peak of the waveform, when current's going to be high, at least with the resistive load, where it would deliver a lot of power. So you might end up with some asymmetry, some distortion. Of course, feedback would clean that up, but you would still clip early. You know, if there's not enough current here, the output stage cannot do its job. So that's about it for the VAS stage. We'll look at the other components in a later video. But I want to take a look at different constant current sources and how they will function. So I have a couple different types of constant current sources drawn here. These are what you would commonly find in an audio amplifier circuit. It's completely unnecessary to use a precision constant current source. These work more than well enough. You don't have to get a precision voltage reference and then use an op amp to generate the constant current. It just doesn't make sense to go through that complexity when something like this is more than adequate. So the basic layout of the circuit, you have a transistor, emitter resistor, a base resistor, because you want to limit the current. You're feeding some voltage into the base here to make the circuit function, and something that gives you a voltage reference. That could be a couple of diodes, Zener diode, very popular to use LED here. In this circuit, we replace that voltage reference with another transistor. The rest of it's set up just the same. To calculate the value of the emitter resistor you want to use, well, you take your voltage reference, in other words, the voltage drop across this device here, minus 0.65 volts, the base emitter diode junction voltage, divided by the current you want to run, and that'll give you the value of this resistor. So how does the circuit work? Well, let's say you got it all figured out and it's running. It's delivering the proper current. So what happens if the voltage across this increases? Well, it wants to pull more current through it. So what's going to happen? The voltage drop across this resistor is going to increase due to that higher current. When you increase the voltage drop, more current is going to shunt through this circuit, because remember, this is a voltage reference. It wants to keep this voltage set at a certain level. So if you increase the voltage across it, it's going to conduct more and shunt current away from this transistor, so less current is flowing through the base. So it's going to decrease the current flowing through here and bring it back into spec. And the converse is true as well. If you put a lower voltage drop across the circuit, it wants to draw less current, so the voltage drop across the emitter resistor decreases. And when you decrease the voltage drop across this, it wants to conduct less, so more current's going to flow through the transistor now and turn it on harder, and it brings that current back up. In this circuit, we replaced our voltage reference with a transistor, but the function is pretty much the same, really. So what happens is, if this is carrying the designed current and you increase the voltage across the device, heavier current's going to want to flow, increasing the voltage drop across this resistor. So more current is going to want to shunt around that resistor through the base emitter junction of this transistor. When that happens, you turn this transistor on more, and it's going to shunt current away through its emitter collector junction around the base emitter junction of this transistor, thus reducing the current, and it brings it back into check. And of course, with less voltage drop, a smaller voltage drop here decreases the current, turning this transistor on less, so it shunts less current. More current's going to go this way, and turn this transistor on more to bring the current back up. But with this transistor being an active device, it should be more precise in its operation due to the effects of feedback. Now, doing some reading, I understand that it is possible for this to oscillate, and that could be a big problem in the amplifier. But I'm going to set up a circuit and do some tests to see how stable it is. So why did I select an LED, more specifically a green LED in this circuit? Well, the reason being is a green LED is supposed to perform really well. It's supposed to have good thermal matching with this transistor to, to keep the current pretty well in check. So it is quite common to see a green LED used in some amplifier designs. Plus, it has a fairly low voltage drop of around 1.8 volts at the current that it's going to be conducting, and we need that low dropout voltage for this circuit to keep it operating properly in the VAS stage. Now this is one of those, I believe it's the phosphide type, the older type green. It has like a lime green color, not the new bright green indium gallium nitride LEDs. Those have a higher voltage, around 2.8 to 3 volts. This is the older LED that has the lower forward voltage drop. So I'm going to set these circuits up on the breadboard and perform some tests to see how these perform. Okay, have them set up on the breadboard. The CCS on the left is the one with the light emitting diode. The circuit here and the double transistor circuit is the one on the right. I have the meter hooked up to it, monitoring the constant current right here in the collector circuit. I have the power supply, this one here, going across the CCS, and this one up here is what's supplying power to the base. So I want to run a few tests. The first test, I'm going to vary the voltage that's going into the base circuit here and see how it affects the output. Then after that, I will run a test by varying the voltage across the CCS and see how it affects the current. And in a third test, I will put a signal on this, a square wave, and look at its performance. Okay, for the first test with the CCS that has the LED, I'm going to vary the voltage going to the base. Now it's set for about 16 volts, and I will drop that down, and it's now about 9 volts or so. You can see it's dropped a little bit. When you change the current across the LED, the voltage drop will change a little bit, which affects the current of the CCS. So keep dropping this. Now it's running about 4 volts. You can see it's dropped 1 milliamp. So I really don't see a huge difference in the current going in here. The resistor I selected of 10K is plenty for this, so I think it'll work fine. It's not going to be an issue in the amplifier because the voltage it's being fed is not going to change much. It might change by a couple volts, so it's not really going to affect that. Plus it's going to be filtered. Okay, now I'm going to adjust the power supply that's fed across the circuit, in other words from this point to this point, and we'll see how it affects the current. This is more important because it'll show the linearity of the circuit, and I also want to see what the dropout voltage is. So we're at 16 volts. I'm going to crank the power supply all the way up to 32. Okay, it's maxed out. Okay, it went up a little bit. It's at 11 now. Okay, I'll bring it back down to 16. I'm sure the transistor gets hot, dissipating more heat, more energy. That affects it somewhat. Okay, we're down at 16. And it pulled it down close to what it was. So now let's go down the other direction. We're at 4 volts, and it's changed a little bit. And I'm going to keep dropping it down to see where its dropout voltage is. So we're at 2 volts now. We're at 1.5 volts. Okay, it's dropping out now. That's 1.2 volts. I'll bring it up. 1.3. 1.4. Yeah, around 1.3 or 4 volts it seems to be back in regulation. And from about 1.5 volts all the way up to 32 volts there was a change of 1 milliamp. So yeah, for being such a simple circuit, it is doing a pretty good job. Not perfect, of course, but good enough for an audio amplifier. I mean, such a small change over such a large voltage, it's not going to cause a lot of distortion. There is some distortion, but nothing serious. Now I move the power supply and the meter over to the dual transistor CCS, and we're at 16 volts on both supplies right now. Now you'll notice this one is lower in current. Again, that's because of the transistors I selected. I don't have one to fine tune it to get it to the same current as the other one, but we can still measure this relative to it, see how it performs. So again, I will adjust the voltage going into the base and see how it affects it. So we're starting at 16 volts. I guess if you want to be technically accurate, it's minus 16 volts. We're using PNP transistors. And we're getting low, about 4 volts. And you can see it does drop quite a bit. Of course, if I turn it all the way down, it pretty much goes off. And again, this is not really critical. I just wanted to see what would happen, because like I say, with the amplifier it's going to be fed a constant voltage and the meter wants to turn off. Okay, now I'm going to test the voltage across the CCS and see how it varies. Something strange happened. This meter turned off by itself, you know, it's auto timeout. When I turned it on, it didn't come back up to the same current it was before. That's weird. But anyway, we're at 16 volts. Crank it all the way to 32. And it's not really changing. So that's very linear so far, so I'll turn this down. Okay, we're at 3 volts. It dropped a little bit. And now I'm going to drop it down and see where it came back up. That's weird. This meter, I'm not sure about this meter. That or there's a funky connection, but let's see what the dropout voltage is. We're at 1 volt. It seems to be still in regulation here. Okay, I think we're dropping out. Yep. That's 0.7 volts, 0.8. It's picking back up. 0.9. Looks like 0.9 volts. That's the dropout voltage. So I'll bring this back up. And it stays in regulation. So it doesn't vary near as much as the other circuit did. And in a way that's expected. I mean, it's supposed to be a better performing circuit having 2 active devices, provided it doesn't break out in oscillations and stuff in use in the circuit. Okay, so the next test, I'll hook up the function generator, the oscilloscope, and we'll do some dynamic tests and see how it performs by putting a square wave across it. Okay, I'm setting the circuit up for the dynamic signal test. So I'm injecting the supply 32 volts, or I guess you can correctly say negative 32 volts, through the 1K resistor. And now the signal generator is coming in on these leads through a 470 ohm resistor. And at this point I'm going to use the scope to measure the signal, taking care to set the probes of the scope into 10x mode. The reason for doing that is it's a fairly high impedance circuit, plus we're dealing with square waves with fast rising edges, and you don't want the capacitance in the probe leads to affect our measurements here. The reason for sending power along with the signal is to make sure there's current flowing at all times in the circuit. The function generator will have a positive and negative going signal, and I want that to be biased towards negative because we want to keep current flowing. Now you might be saying, don't your function generator have a DC offset that you could use? Yes, it does. However, to get the full peak-to-peak voltage I need to drive this with, I can't really use that. So I'm just going to send the signal along with some power supply voltage to offset the signal to keep this turned on during the full cycle of this waveform. I'm using my Fieldtech arbitrary signal generator. Just lovely Chinesium quality here. Wonderful piece of gear. So let me get the camera pointed to the scope and in focus, and we'll start taking measurements. Okay. Measuring the waveform. I'm DC coupled and going with the scope probe on the most negative point for its ground and probing at that point I showed on the schematic, which of course would be more positive, so that's the square wave. I am DC coupled, so let me go to AC so we can see. I can turn this up more. You can see there is a little bit of a peak, but that is from the signal generator. See if I put that on there. Let me turn this down first. See, that's from the signal generator. Lovely quality signal generator. Okay, we're back on the current source. So you can see it's doing that on both sides, but again, signal generator. So let me crank this up. And that's the slew rate. We're at 50 nanoseconds. And let me check here. I gotta turn that down and measure the signal coming out. Okay. A little bit slower at the current source. I don't know, is it really? Let me check again. So if I put that peak right there, it's like, I don't know, 2/3. Let me go back. Turn this back up. Now, of course, that's wider. So, yeah, it's roughly the same, I guess. Now, some of that crap you see here, that's from the signal generator, I do believe. Yeah, see, that's the signal generator. A little bit of ring. Not really the fault of the current source. What's with this jitter? Oh, that's why. Get that back there. Okay, I moved over to the dual transistor CCS, and, well, it's looking quite a bit the same. 50 nanoseconds. 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 50 Let me crank this up. Look at the... There might be a little bit of ringing here. Let me turn that down and move over to the signal generator's output. See what it's actually doing. It's not perfect, but different sort of ringing, I guess. Yep. So yeah, there could be a slight oscillation with this circuit. Okay, what about the slew rate? Okay, we're at 50 nanoseconds just like we were before. And yeah, I don't really see any difference there. You know, I should also look at the negative going slope. I didn't show it on video, but it's the same as the other one. So yeah, not a big difference. If I can grab the right knob there. You got to grab the right knob. So we bring this up to its normal operating voltage and getting a little bit of ringing. Okay, so now I'm back on the LED CCS on the falling part of the square wave. This junk is mainly from the function generator. It's not oscillating like the other one did. And at 50 you can see the slew rate's about the same. So yeah, I'm kind of getting scared off that dual transistor circuit. It could be the breadboard. You know, these breadboards aren't that great. But being with two active devices, it could be a potential for oscillation there. So I might go with the LED based CCS, even though it doesn't track as nice as this one does. But in an audio amplifier, I'm not sure that it's so critical. I don't know. Like I say, engineers out there, audio amp designers, I know some of you watch the channel. What do you think? Like I say, it just could be parasitics on the breadboard here. These aren't ideal. Not a lot of current in this circuit though. But with that fast changing edge on the waveform, yeah, it could be an issue. Well, I'm going to leave it at that and wrap up the video. Do appreciate everybody watching and stay tuned for more. Field Tech. Okay, I'm going to cut all that shit out. That's just bullshit.